Yeah, great. Thank you, Madi. So very happy to give the second lecture here. So today, what I was planning to tell you about is so yesterday what we saw is we introduced some motivation for like an inflationary period in the early universe, and sort of how to describe it also from an effective field theory point of view. And then two things that are important about what we saw yesterday is that one way to think about inflation is as a quasi-de Sitter space. So we saw that we could generate a period of inflation by having a slowly rolling scalar field, where sort of the dynamics is very similar to the Sitter space, but then there's this slight evolution in the scalar field, so it's slowly rolling, which brings you slightly away from the Sitter space. And then the second thing that we saw that was very important is when we try to describe inflation from sort of an EFT point of view, so sort of being agnostic about particular UV dynamics that are happening, then we saw that inflation is UV sensitive. And in particular, what we saw is when we did this sort of EFT approach to inflation, we encountered the so-called eta problem, which was the issue that when we think about this eta parameter, which is one of the slow roll parameters, so we typically want that to be very small, is when we sort of consider a natural leading high dimensional operator, as sort of EFT tells us that we should include. And this gave a contribution that is potentially very large and therefore can spoil inflation. And what this did for us is this sort of motivated going beyond sort of this EFT type of perspective, or at least sort of trying to understand if there are some certain symmetries in the UV that can sort of prevent these large and dangerous corrections. So what we want to understand is sort of what are these constraints that quantum gravity can put either on an EFT of inflation or maybe more general even the Sitter space. So maybe before I sort of start the main theme of today, maybe let me pause a bit to ask if there are questions about yesterday's lecture, if there are particular things that you thought were unclear. So feel free to ask me that. Okay, if there are no particular questions, then we can continue. So the main theme of what I want to tell you today about is sort of how can we have sort of a well-motivated model of inflation, sort of coming from perhaps some string theory dynamics in the UV, and sort of see what type of constraints can quantum gravity put on such type of models, and what sort of implications could it have for observations. So sort of the particular inflation candidate that I would like to tell you about today is an axion, which are very interesting inflationary candidates because they enjoy such symmetries that seems to protect you from receiving large corrections. And they're also very well motivated from a string theory point of view. So sort of the name of the game is what we want to do is we want to evade the eta problem. What we want to do is we need to have a particular model with symmetries that are respected in the UV. In the UV, such that large corrections are prevented. So what is a natural candidate? Well, as I just told you about, a natural candidate are axions. So what are axions? Well, one way how they can arise, also, for example, in string theory, is when you integrate, arise from integrating a P-form gauge field over a P cycle. So what that looks like, for example, we can have let's say that we have an action that we call A. Then the way it arises is we take some particular, in this case, a two-form gauge field, and we integrate it over a two-cycle. So this, for example, in string theory, you can have different p-form gauge fields. So this is one way, if that wraps a cycle, how such an action could arise. So these are scalar fields, so they are inflaton candidates. And in particular, what is important is that they have a shift symmetry, which arises from the gauge symmetry of the gauge field that were considered. So we have the gauge symmetry that looks as follows. So we can send A2 to A2 plus some constant parameter, exterior derivative on that. And then what happens is that because there's this gauge symmetry for the p-form gauge field, then this action has a shift symmetry that looks as follows. Now, the fact that we have the shift symmetry on this action, this really offers a very strong projection. Because now if we want to write down our EFT for this action, then the only things that the operators that we can write down that would correct, for example, eta, would have to be derivatively coupled in order to make sure that the shift symmetry is respected. What is nice is what happens for the shift symmetry. It is has been shown in a few papers a long time ago, for example, by Wen and Witten in 86. Another paper by just Witten in 86, and Dine and Seiberg in 86. It's productive here. That is a shift symmetry of the action. It's preserved by perturbative effects, so you can sort of write down all possible perturbative effects, and you can always show that this respects the shift symmetry of the action. And it's only by non-perturbative effects, for example, like instantons, that break this shift symmetry down to a discrete shift symmetry. If you consider a particular action or an instanton effect that breaks this perturbative shift symmetry, then the shift symmetry of the action is broken to this discrete shift symmetry. Okay. So let's say that we're sort of considering an expansion in possible instanton effects. We're imagining the situation that we are sort of just looking at the leading instanton correction that gives this breaking to this discrete shift symmetry. Then we get the following EFT for the action. So here I transform to a canonical scalar field, which is defined as follows. I'll tell you in a moment what this F is. So there are some mass scale, and that sort of depends on the precise dynamics of this instanton. And then you get a cosine looping potential. Okay, so this F is typically called the axion decay constant. You can think of it as sort of as the analogous coupling constant if you have like a gauge coupling G, and this is sort of the analogous coupling for this axion, how it couples to this instanton. Now, in terms of this canonical scalar field, what we now have is a discrete shift symmetry that looks as follows. Okay, so now it's of course interesting to ask what does this potential look like? So what we get is when we plot this potential for the axion. What we get is something that looks like this. So we have this cosine looping potential where this width is given by 2 pi squared. So of course now we want to understand, okay, so we see this potential that has like this oscillating behavior. And of course, if you want to drive an inflationary period by having such a potential, what we saw yesterday is that we want to make sure that this potential is sufficiently flat enough, which would correspond to having this axion decay constant parameter to be sufficiently large. So let's say, for example, that we look at the eta parameter, which can be expressed in terms of the potential as follows, where these apostrophes denote derivatives with respect to the field. So when you look at this cosine looking potential, you find that this eta parameter is proportional to m squared over s squared, and we want to make sure that this is sufficiently small. So in terms of the axion decay constant, what that implies is that f is sufficiently large with respect to the Planck scale. Okay, so in that sense, these axions, they make a very good inflationary candidate because they naturally have this shift symmetry, which is really only broken by small non-perturbative effects. And what is even more is what seems to happen is that you can have what is known as a model of inflation that is large field. Because if you look at sort of the distance that the scalar field or the axion traverses in field space, it becomes larger than the Planck mass, which has some interesting consequences. So let me tell you what these consequences are. So just said is when we have f over m Planck to be sufficiently large, we can have a trans-Planckian model of inflation. So now, why this is an interesting model of inflation when you have such a trans-Planckian or said similarly a large field model of inflation, because this has very important observational consequences. So at least if we sort of assume that inflation was sort of at least dominated by a single field like this axion model, then what this leads to is observable primordial gravitational waves. So what these would correspond to are sort of tensor fluctuations or metric fluctuations in the early universe that got stretched by inflation and then leave an observable imprint on the CMB that we could measure. And this was first realized in a very famous paper by Lars. So this is known as the light bound. So let's go into that. So yesterday we sort of saw this classical picture of inflation where we sort of just considered the classical dynamics where there's this scalar field that is slowly rolling. But of course you can also, or what's important that you also include sort of quantum effects in the early universe. And sort of two important fluctuations that you consider are scalar fluctuations. So we can roughly think of them as fluctuations in the inflaton. So just imagine there's some sort of uncertainty in the position of the inflaton during inflation. And what happens is that these type of sort of scalar fluctuations, those are the ones that are responsible for leading to temperature fluctuations in the CMB. In addition, we can also have tensor fluctuations, which you can roughly think about as sort of quantum fluctuations in the metric itself. So those would be tensor perturbations. And these are the ones that lead to primordial gravitational waves. And typically, the way these tensor fluctuations or these primordial gravitational waves are parameterized is by the so-called R parameter. So if you look at, for example, constraints on inflation by Planck data, they typically give you value, for example, for this R parameter, which is known as the tensor to scalar ratio. So it's defined as the amplitude of the tensor fluctuations divided by the scalar fluctuations, where with the amplitude we typically mean something proportional to the 2-point correlation function. So for tensor, it would be something like, very roughly something like this, where we don't worry too much about the tensor structure. Okay, so what Light realized in this paper is that sort of this precise value of R, so the amount of gravitational waves that you can see from inflation, is directly correlated to sort of the distance in field space that the inflaton traverses. So when we are looking at single field inflation, there's a relationship between this tensor to scalar ratio and the first slow roll parameter epsilon that we saw yesterday, which basically measures the shallowness of the potential. So R is given by 16 epsilon. So what we can do is we can now, from this epsilon parameter, by expressing it in terms of the particular potential that is driving inflation, we can derive the following relationship. So a derivative with respect to n, where n is known as the number of e-volts, which is defined as follows. So it's the derivative with respect to time. So it basically the amount, so we typically say it's the amount of e-volts that are elapsing during inflation. So you can think of it as a number of Hubble times that inflation lasts. And of course, what's important to note here is that we have this vector of m Planck squared here. So typically what this means is that primordial gravitational waves are Planck suppressed. Okay, so let's say that we now have schematically a potential that looks as follows. And what we can do is we can relate this tensor to scalar ratio to the amount of inflation or the amount of field distance that the inflaton has traversed. Okay, so it's schematic. So here we have some inflaton potential. And then what we're imagining is that at some point inflation ended because let's say that the potential became too steep. Let's say that has happened here. Here we have some particular scale phi star, which we sort of can identify. And that's at some point what happens during inflation is that these modes get stretched, they re-enter the horizon, and at some point they can leave their imprint on the CMB. So we're imagining that phi star is sort of the scale at which particular modes could leave their imprint on the CMB. So now the amount of field distance traversed can be expressed as follows. So delta phi divided by m Planck. We integrate now over the number of e-volts. So it's useful in order to sort of solve this integral is to derive what we call sort of the effective number of e-volts, which is defined as follows. Right here, R star is the value of R at this scale star, so scale phi star, I guess. Okay, so it sort of depends a bit how much e-volts you need in order to have sort of a successful period of inflation and solve these sort of classical problems that we talked about yesterday. So depending on the precise model, the range of e-volts can vary a little bit, but sort of a reasonable value that you can often see quoted in the literature is like an effective to be roughly 50 e-volts to sort of solve your standard cosmology problems. So when you plug that in, as you find the following relationship between the field distance traversed during inflation and the tensor to scalar ratio. 0.03 and square root. Okay, so currently, I mean, there are constraints on the amount of primordial gravitational waves that we see. We haven't observed them yet, but there are constraints. And I think the current one of the, if you combine a few experimental results, I think roughly the tightest bound is roughly like R is smaller than 0.04. So this is the current bound. And sort of by the end of the decade, we expected sort of experimental results would be able to push the tensor to scalar ratio down to something like of the order of 10 to the minus 3. So if you would plug that in, let's say that we sort of observe primordial gravitational wave at this level, what would that imply? It would imply that delta phi divided by m Planck is roughly 1/2. So this will be having a field distance that is pretty close to the Planck scale, which of course would be huge, because what it means is that we could really use sort of inflation as a probe to physics that is very close to the Planck scale. And as you might remember, so around 2014, there was this BICEP experiment that initially thought they had measured this tensor to scalar ratio at like a value of 0.2. And this would be like crazy huge. So that would mean that you really have a very transplanar model of inflation. It turned out that, I mean, this was a very difficult measurement to do, as that the measurement was not done entirely correct, or they measured these sort of these primordial or they measured a signal, but this was not from primordial gravitational waves. So this has been ruled out. But still, so this is a very important question that sort of connects quantum gravity to really observational consequences. Because if we would measure these primordial gravitational waves, it suggests that there's sort of an access to physics that is very close to the Planck scale. If you now sort of come back to our model of inflation that we saw, axion inflation, for this particular model, whether or not we see these primordial gravitational waves is closely related to having f bigger than m Planck or not. So if you have f bigger than m Planck, we can have this transplankian model of inflation. We could potentially see primordial gravitational waves and really probe quantum gravity effects. But from how I'm presenting it, you might already think, is there a catch or not? And what I now would like to talk about is sort of what constraints quantum gravity puts on F. Because naively, you might sort of say, oh, from sort of an EFT point of view, it might seem a bit strange that they have sort of this particular parameter, which is transplanckian. Isn't that sort of unleashing all possible Planck suppressed operators? But naively, it seems to be okay, because there's this axionic shift symmetry that is only broken by small non-perturbative effects. So you might say that this model is under control. It turns out that the weak gravity conjecture does seem to put constraints on this axion decay concept. So let me move to that next, but maybe I should stop briefly for questions about sort of this light band. Yes, there's a question.
So I'm a little confused why we need eta much smaller than 1, because we could either have, I mean, epsilon much smaller than 1 or the other constraint. So you have assumed that eta is much smaller than 1, right?
Yeah, exactly. Indeed, so the reason why we want sort of both these slow parameters to be small, so both epsilon and eta. So epsilon sort of measures the shallowness of the potential. And then eta is basically sort of the derivative of this first epsilon parameter. So if you only have epsilon small, but not necessarily eta, what would happen is that you would only have a very short period of inflation. So what would happen is that the potential is sort of shallow at a point, but then quickly it becomes too steep. So that would only generate a very low amount of e-volts of inflation. And typically, in order to sort of solve this horizon problem, we need to have an appreciable amount of period of inflation.
Yes, so it's not because of Swampland constraint, it's an observational bound. Because, I mean, we need epsilon small, then we need eta small. So I thought it's because of the Swampland constraints, so it's not so.
That's a good question indeed. So this is sort of an observational constraint. So indeed, so what we're sort of assuming is that there's this period of inflation, and what we need to generate it. To generate it, we need to have sort of small epsilon and small eta. But I think you're right in saying that when we think about the Swampland, there are sometimes also constraints on potentials that appear. And And they sort of go sort of the opposite direction. So they are a bit in tension with this slow roll result, because they typically say that the potential cannot be too shallow. But they haven't really talked about that yet. And I think we'll come to that.
Thank you.
Yeah, thanks for the question. Okay. So now what we want to tell you about is sort of how the weak gravity conjecture, how can that possibly constrain this action decay constant, and sort of see if we can have some model of large field inflation using axions. So I presume that you have already seen a bit about the weak gravity conjecture in other lectures. So this is sort of a slight generalization of that that applies to axions. So what you might have seen is that what the weak gravity conjecture tells you, the weak gravity conjecture bounds the particle spectrum of EFTs. And in particular, what we can do, so sort of the standard form of the weak gravity conjecture, or the first form of it applies to one-form gauge field, so sort of like electromagnetism, but you can also generalize it for p-form gauge fields. And then what the weak gravity conjecture tells you is that for a p-form gauge field, there must exist a p-1 form brane. Such that the charge to tension ratio of this object is bigger or equal than the charge to tension ratio of an extremal object. Where what we mean by extremal can depend a little bit on the theory that we're looking at. So sort of the standard weak gravity conjecture, we're typically thinking about one-form gauge fields. So the particles that are charged under that, or the states that are charged under that are particles. And then in this case, what happens is we have a charge to mass ratio, and the extremal objects that we're thinking about are black holes. So in particular, in order sort of to correctly formulate this conjecture, we need to have a notion of an extremality bound. So when we think about higher dimensional gauge fields, for example, you can have black brane objects that would be the extremal objects that we're considering. But what happens is there's a special case if we take p equal to 0. So then sort of the zero form gauge field that we have in between quotes will be an axion. Then sort of the -1 form brane that we have would be a instanton. So here you directly see the connection to this axion inflation model, where this potential was generated by instantons, and sort of the precise details of those effects would determine if we can have this large field model of inflation. So if we apply the weak gravity conjecture to such a setup, what we expect is a bound that roughly looks as follows. So we have some sort of instantonic charge. And then there's sort of this analogous of the gauge coupling, 1 over F. Then there's the action of the instanton in this case, which is sort of the analogous quantity of the tension. This should then be bigger or equal than this ratio evaluated at some sort of extremal solution. Okay, so this is, so in this case, we can define the instantonic charge as follows. It's sort of just the analogous way how you would define a charge for a higher form gauge field. So you take some integral, in this case, there's this coupling that is appearing, integrated over some d-1 sphere, and then you take the H star of the exterior derivative of your gauge field. So let's say that you would define this charge for sort of standard electromagnetism, and then this will be star F, where F is the field strength, and we can write F as dA, where A in that case would be the one-form gauge potential. Okay, so given this sort of zero form version of the weak gravity conjecture, the action on weak gravity conjecture states the following. Let's say that I'm given an axion with decay constant f. And I want to couple this system to quantum gravity in order to approach the Swampland. Then the axion weak gravity conjecture tells you is that there must exist an axion such that the following bound is true. So there's a blink appearing, which I did not write down in the previous inequality. F action of the instanton should be bigger or approximately equal than 1. Okay, so what's happening now is that it is slightly less clear than what happens for the for sort of the higher form weak gravity conjecture, because now I'm not very precise about sort of what the order 1 number is. And the reason for that is that there's not a natural notion for sort of the extremal objects or the extremal instantons that you can consider. Because what happens is you can try to look sort of for these gravitational instanton solutions and sort of see if there's a notion of extremality. What you then find is there could be different possible contributions, and it's not sort of clear which one is the correct one that you want to normalize the weak gravity conjecture with. So typically this statement is precise up to this order 1 constant. So let me give you a bit more details on that. So what are these instantons that we're looking at? Well, these would be gravitational instantons. Which you can think about gravitational configurations that solve the Euclidean equations of motion, so the Euclidean Einstein equations. So what we want to do is when we want to search for the sort of possible extremal instantons, is we want to look for Euclidean solutions. To general relativity coupled to the action. So when you do that, when you look at the action of the Einstein-Hilbert action, and you have this actional field, and then you can find the following metric solution that solves the equations of motion. So here I just give you the form of the metric. So C is some particular constant. It can take different values. And here the omega squared is sort of the is part of the metric sort of on the round d-1 sphere. So then sort of depending on this precise value that C can take, you can have different type of solutions. So you can what is known as chord solutions. So these are configurations that have a singular core. So in that sense, they already look a bit funky, I guess, because you have a singularity there. So it's sort of a question if you just need to sort of regulate the singularity, or that you should discard them completely altogether. Like could they be resolved in string theory? And that is not completely clear at the moment. So this is sort of one solution that you could try to look at. There's also one that is typically known as the extremal solution, which seems reasonable because it has the word extremal in it. So that's sort of typically schematically takes the following form. So it doesn't have like a curvature that generates a throat. And then finally, if you take C to be negative, then there are wormhole solutions. So these are solutions with a throat, but they do not become singular. So schematically, they look as follows. So what you could imagine for the wormhole solution is you could take such a configuration, glue another one such configuration to it, and then it's clear why this typically are called wormholes, because now you can have two asymptotic regions where you can that are connected by this wormhole throat. Okay, so you can try to compute the action for all these different solutions, which is a bit tricky because you need to worry a bit about the regularization. For example, in these singular solutions, the bottom line is that what these different configurations do to you is that they typically give different order one contributions to the action. And what is more, so you might say, oh, perhaps I can just consider sort of this natural notion of extremality and use that to sort of define my action regravity conjecture. But then it turns out that in some cases, sort of these other configurations, they can have a lower action. So that would typically give the dominant contribution to the instanton potential. I think the situation has not been completely settled yet. And it's sort of an ongoing debate what the correct way is of sort of normalizing this order one factor in the action regravity conjecture. So I think sort of the best approach you can take at the moment is to be sort of slightly ignorant about this precise order one factor and just try to sort of derive parametric statements that are not super sensitive to this precise order one value, which is what we're going to do in a moment. So sort of the best that you can do is we know that sort of the value of the action for sort of this extremal configuration is of the order of Q instanton divided by F times something. So when we sort of take this as our notion of the action regravity conjecture, we arrive at the bound that we saw previously. Wave swap one over and plane. So this is sort of the action regravity conjecture that we will be interested in. Okay, so now what we want to understand is sort of we have this particular bound that arises from the regravity conjecture. And then it's of course a question how this constrains the action decay constant, because that's the quantity that was interesting for action inflation. So we can rewrite this, of course, by saying that the action decay constant should be bounded as follows. This is just a simple rewriting. And now let us see sort of how this constrains the action potential. So in general, the action potential, so first I just gave you a schematic form where we looked at sort of the action with the charge that is normalized to 1. But in general, what will happen is that the action potential will take the following form. So there's a suppression that is given. Now I should write this as I to be consistent. So it gives a suppression with the instanton action. So the larger the instanton action is, the smaller is the contribution to the potential. And in general, as we saw, this instanton action depends on the charge. And then we can have this cosine term. But then when we write this for a general instantonic charge, there's a factor of Q that appears in the cosine. And this has important consequences. So let's say that there are sort of these instantons that contribute that have a charge bigger than 1, then you get a potential that can look roughly as follows. So let's say that we're first just looking at sort of the unit charge potential contribution, which is the one that we saw before. So this would have Q equal to 1. But then, of course, we can also consider a higher charged instanton, which then has a periodicity that is smaller. So it would look something like this. So this would have Q instanton equal to 2. then what happens, so let's say that this particular instanton gives an equivalent contribution as the unit charge instanton. Of course, what happens is that you might start out with a very nice flat potential that satisfies sort of your conditions to generate inflation, but then there's this higher harmonic that would be added to the potential. So if you start out with a nice flat potential, then this would ruin your flatness. So sort of the lesson here is that if you have these higher instanton contributions, this leads to higher harmonics. And typically destroy the flatness of your potential. Okay, so what we want to make sure is that when we're drawing such potential, we want to make sure that we can just focus on sort of this leading contribution. So in order for that to happen is because this instanton action takes a particular value and is proportional to the charge of the instanton. What we want to make sure is that this instanton action is very large. That way, when this instanton action is very large, then we can sort of suppress these higher harmonics and we can just sort of focus on this leading instanton correction. But then when we look at what happens from our action V gravity conjecture bound here, and we look at this leading contribution, which has unit instantonic charge, then this implies that F should be much smaller than M Planck. So this is precisely the opposite regime that we could use to generate inflation with that potential. So it seems to be saying that if we can sort of believe at least these parametric arguments, that the axion V gravity conjecture does not support large field inflation with actions. Of course, these arguments are somewhat parametric, and I think it's always good to go to explicit examples and try to see, can we find axion decay constants that will be larger than that? And typically, I think the answer seems to be that if you at least look at sort of the single field axion inflation model, then there are no axion decay constants known that are much larger than M Planck. And of course, it's a bit difficult to say sort of what is the precise cutoff, like, do you think that 0.8 M Planck is big or not? So this is sort of a question that depends on the precise details. But sort of at least as a parametric statement, it seems that large field inflation using axions is in tension with the axion V gravity conjecture. And sometimes people take this a step further by taking this as an evidence that more generally, quantum gravity is incompatible with large field inflation. Maybe I should add a question mark there. Because this is, of course, something that would have huge consequences if true. And I don't think we're yet in a position to really have such a sharp statement. So the consequences would be, if this is true, then there will be no primordial gravitational waves from inflation. But in order to reach this point, I think where we can really say this confidently, there are still these open questions. For example, we need to fix this order 1 coefficient that appears in the axion V gravity conjecture. And presumably people have played games where you can try to look at multiple axion contributions, so sort of have a multi-field type of model, and then try to find ways around this. And I think it's fair to say that it's still an ongoing debate if this is possible or not. But it's definitely clear that if you want to have such a large field model of inflation, you need to work very hard. So that's what people have motivated people to try to consider explicit string theory examples and see if we can construct such axion inflation type of models. And I think the jury is still out on that. So that roughly brings me to the end of today. So let me just briefly recap sort of what we saw today. So what we learned today is we try to find a way to basically to protect inflation from having large corrections. And the natural sort of notion of what you might want to use are symmetries. In particular, you want to use symmetries that are present in the UV. So axions in principle are a very good candidate. Because they naturally have the shift symmetries that are only broken by small non-perturbative effects. And in particular, if we at least look at a sort of single field axion model, then they even seem to support large field inflation. However, what happens is that these axion decay constants are constrained by Swampland conjectures. What it suggests is that when we think about these axionic inflation models, is that they does not seem to support large field inflation. And so, and this, if this is true more generally, then you might be suspected to lead, okay, if we want to generate a period of inflation, then perhaps it cannot be this large field model, which is a bit of a shame, perhaps, because it would say that whatever the energy scale is that inflation happened at, it might not be very close to the Planck scale. But at the same time, of course, it's true that these Swampland conjectures, they seem to tell us that there are certain effects that are much lower than the Planck scale. So perhaps it's not such a bad situation after all. Maybe we should try to consider small field models of inflation. But I think more general, and this brings me sort of to what we'll talk about in tomorrow's lecture, is perhaps we want to also understand a bit better, are there more generic constraints that don't necessarily apply to sort of, for example, this large field inflation model, but constraints on the Sitter space itself. So sort of any, or quasi the Sitter space, or any sort of inflationary type of setup, could we find constraints on that? So that is what we'll talk about tomorrow, is the Sitter space and the Swampland. Okay, so it brings me to the end. I think we still have like about 10 minutes left, so I will be happy to discuss a bit more and take some questions if you have any.
Thank you very much. Thanks. We have time for questions.
I have a question.
Please.
So if I understand correctly, gravity conjecture requires existence of at least one axion satisfying the inequality, not all axions. So what if the axion which gives dominant contribution to the inflationary potential does not satisfy this inequality?
Yeah, that's an excellent question. and that is, I think, something that people also have considered. So indeed, so I think it's fair to say that for the axion weak gravity conjecture, it's not completely clear what sort of the correct version of the conjecture is. So we have this order 1 coefficient, but then also, as you said, there could be the case that there's just one axion that satisfies, one instanton that satisfies it. And you could have another instanton that would give a more dominant contribution to generate large field inflation. So I think sort of this distinction is the same distinction for sort of the particle weak gravity conjecture, because there you can have a similar situation where you could say there's just one particle that satisfies the weak gravity conjecture. It can have a very high mass, and it would not be really relevant what happens in the IR. So said differently, you could have sort of this very large state that satisfies, very heavy state that satisfies the weak gravity conjecture, but it could have very negligible consequences on your EFT. So I think, at least for the particle weak gravity conjecture, we have quite some evidence that sort of stronger versions of the weak gravity conjecture hold. So that those typically go under the name of like the tower weak gravity conjecture or the sublattice weak gravity conjecture. And And I think it's not completely clear, but there is some evidence that something similar like that should also happen for axions. So if that can be made very rigorous, then that would sort of close that particular loophole that you're considering. But I think it's fair to say that it's something that has not been completely settled yet. So as of yet, I think that's a fair criticism to have.
Okay, thank you.
Other questions? Yes, please.
So I had a question about details. So what was C in the metric that you mentioned about, the C in terms of other parameters, like the Q center? Yes.
Yeah. Let's see. I think I can't give at the moment a really sharp interpretation of it. So what happens is that basically you can try to look for different type of solutions to sort of GR coupled to this dilaton or this axion. And then what happens is that C is sort of a parameter. I guess it sort of appears as an integration constant in your equations of motion. So there are different solutions for arbitrary C basically. So sort of on a technical level, I guess you can say it's an integration constant. I guess there must be a sort of also a more physical interpretation. So typically if you solve like Einstein equations, you have constants like this, typically they can be related, for example, to the two mass parameters. Maybe I can come back to that tomorrow. But I think so on a technical level, it's an integration constant, but I guess it has a nice physical interpretation. But I don't know that on the top of my head.
Yes, thank you. So if it's, we consider the extremality here, that's C0, and is that, was this the logic? Yes. Okay, thank you.
Maybe I can ask one question. So, how axial monodromy works in this picture? So it is also ruled out, or there is a hope to have some kind of monodromy model?
Yeah. So I think indeed it's axial monodromy naively seems to be evade these type of constraints. So I think people have tried to consider could be sort of different type of back reaction effects that that lead to corrections to sort of the axial monodromy potential. I'm not completely sure what the current status of that is. But naively, indeed, it seems to be sort of violating some, at least the spirit of some of these Swampland conjectures. So if you, for example, think about a distance conjecture, I guess that's maybe a slightly more general way how you could try to have constraints on potentials. And sort of if you would try to apply the distance conjecture to such a model, there's an effective, very large distance that you're traversing. So you would expect that there are at least some states that become light in that respect. I'm not completely sure if those have explicitly been identified in axial monodromy models.
All right, so I don't see any more questions. So thank you again, Lars, and we come back tomorrow.
Yeah, thanks a lot. So tomorrow, the sitter space, one of my favorite subjects, so don't miss it.
Thank you.